It's game-based and based on games that you might even play or ideas that you might even have regarding the expected value. So expected value is the average gain or loss of an event if the procedure is repeated many times. We can compute the expected value by multiplying each outcome by the probability of that outcome and then adding up all of our products together. So let's say we have this standard deck of cards and we're going to play this game. You draw one card from a standard deck of playing cards. If you pick a heart, you will win $10. If you pick a face card, which is not a heart, you win $8. If you pick any other card, you lose $6. What is the expected value of playing this game? So in this game, we're just going to be winning or losing money. However, it's not a pay-to-play game. So we'll talk about what that looks like in an upcoming example. So we have 3 different outcomes here. We have an outcome that will win $10. We have an outcome if we win $8, and then the outcome of losing $6. So for convenience, I just grabbed a picture of a deck of cards to help us out here. So our first probability is we will win $10 if we pick a heart. Well, there are 13 out of 52 heart cards. So if we pick any of those 13 out of 52 heart cards, we'll win $10. Now we'll win $8 if we pick a face card that is not a heart. So our face cards that are not a heart are these 3. Here's 3 more, so 6. And 9 out of 52 that are not are face cards that are not a heart. And then if we pick any other card that we haven't yet circled, so there's 10 here, 10 and 10, the 30, if we pick any of those other cards, we will lose $6. So all the cards have been accounted for. And of course, we have 100% probability when we add all of our probabilities together. So we should just make note that we have accounted for all 52 out of 52 cards. And so then we'll multiply these together. So $10 times 13 over 52 gives us 130 over 52. 8 times 9 over 52 is 72 over 52. And negative 6 times 30 is negative 180 over 52. So now when we add all of these together, we're going to add our products together. We end up with 22 out of 52. Or because we're talking in money, about 42 cents we can expect to win when we play this game, especially over long periods of time. Since the expected value is positive, it is our advantage to play this game because we would typically win within the game. Now, our second example, you have to pay $10 to play the following game of chance. So now we have to pay to play. There is a bag containing 12 balls. 5 are red, 3 are green, and the rest are yellow. So I'll just figure this out. We have 5, 8, so that means 4 of them have to be yellow. You are to draw 1 ball from the bag. We'll win $14 if you draw a red ball, and you'll win $12 if you draw a yellow ball. How much do you expect to win or lose if you play this game 100 times? So our outcome is a little different because we are expected to pay $10 every time we play. So I have the outcome of $14, but we had to pay $10 to play, so my net outcome would be $4. The alternative option was $12 that we would win, but if we're paying $10, our net would be $2. And then the other one, we're not winning anything, but we're still paying $10 to play, so I have a loss of $10 if we have this option. So we will win $14 if we do a red ball. So there are 5 out of 12 that are red. We'll win $12 if we draw a yellow. So we found yellow would be 4 out of 12. And then the remaining balls are green, so this must be green. Again, so that we would have 12 out of 12 balls all accounted for. We'll go ahead and multiply, giving us 20 twelfths, 8 twelfths, and negative 30 twelfths. When we add all of these together, we have negative 2 twelfths, so a loss this time, but we're multiplying this by 100 games. So if we were to do this 100 times, what would we expect? Well, then we would expect negative 200 twelfths, or of course, since this is money, we want to translate this into dollars, so negative $16.67. This would not be to our advantage to play this game because we would expect to continuously lose, especially if we played over 100 times. It's also interesting to talk about what it means to be a fair game. So if the result that we ended up with here and on the last one was a positive, if we ended up with a value of 0, we call this a fair game since neither side has an advantage, the player or the receiver of the game. So let's talk about what that might look like in a different situation. A detective figures that he has a 1 in 9 chance of recovering stolen property. His out-of-pocket expenses for the investigation are $9,000. If he has paid his fee only, if he recovers the stolen property, what should the charge be of his clients in order to break even? So our first outcome is we don't know what his break-even point is, right? We don't know, he'll get his money back, but we don't know what he's going to earn in order to do that. So I'm going to say X minus 9,000 when the probability is 1/9. So this is recovering. If he doesn't recover anything, he's lost $9,000. And the chances of not recovering must be 8/9. We still are going to multiply these together. So I'll have 1/9 times X minus 9,000 plus 8/9 times negative 9,000. What does this equal? We need it to equal 0 because 0 is the break even. It's fair in that case. So in order to solve this, I'll go ahead and use some algebra. So I'll distribute. We'll have 1/9 X minus 1,000 when I take 1/9 times the negative 9,000. Here we'll simplify, so I'll have negative 8,000 equal to 0. I now have 1/9 X minus 9,000 when I combine like terms equals 0. 1/9 equals 9,000. Multiply both sides by 9. X is $81,000. So we must charge clients $81,000 in order to break even. And of course, if you wanted to, you could substitute 81,000 into here, subtract 9,000, multiply, and when you add, your expected value should get back down to 0, the break-even point. There are a couple of additional examples. These examples were not from the textbook. There are textbook examples in My Open Math. Their video from the publisher for those textbook examples are there. I just wanted to give you a few additional examples that you could utilize in